Welcome back everyone. In this lecture, we will actually state and prove the Schur's lemma, and we will see some of its applications. So, what is Schur's lemma? Like, even though it is very basic result, since it has been used in many places in representation theory, so it is important to actually kind of give a name. So, Schur indeed he used in his thesis this important fact, and then he realized that this is actually somewhat very important to deduce many results in the representation theory. So, that is why it is named after Schur. So, let us actually state the lemma. It is very simple if you think about it. So, let us start with two irreducible G modules. Okay, let us say V and W be irreducible G module. So, now we are interested in understanding non-zero maps between them. Okay. Let us say phi is a non-zero G module map, non-zero G module map. Okay. So, then it is immediate that the kernel and the image both are submodules in respectively V and W. Okay. They are G submodules in V and W respectively. Okay. So, that means if we take the kernel, so phi is being sorry. So, the kernel and image are being G submodules. So, one can immediately conclude something about them because V and W are irreducible. So, the kernel has to be either 0 or V, and similarly the image either it is 0 or W. So, that is immediate. Okay. So, now kernel cannot be V because we have assumed that phi is being non-zero map. So, that means kernel cannot be V, and similarly if you look at the image, it cannot be 0. Again, if it is 0, then it becomes 0 map. So, this cannot be the case. So, that means the kernel is trivial and image is full. That means phi must be isomorphism. So, this implies that phi is an isomorphism. Okay. So, basically this is what Schur's lemma. From this immediately one can write down the following statements. So, given two irreducible modules, if you take a non-zero map from V to W, that must be an isomorphism. So, that is what Schur's lemma says. From this you can immediately conclude that if V is not isomorphic to W, so then look at this home space, which is set of all G modules map from V to W. So, that must be 0. Okay, this is immediate, and similarly if we take W to be capital V, then this home space indeed given by just the identity, spanned by the identity map. Okay. And the third statement, if we take V to be isomorphic to W, okay, then the dimension of this space VW, home GVW, that must be 1. Okay. The first statement is immediate from the previous analysis. If V is a non-zero map from V to W, then the forces that V must be isomorphic to W. Now, let us look at the second statement and then see what one can prove. So, we already have identity, which is a G module map. Now, if we take any other phi which is a non-zero map from V to V, let us say it is a non-zero G module map. So, then because we are working over complex number, there should be some eigenvalue for this map phi. So, let us say lambda being eigenvalue for the map phi. So, we are always assuming that our spaces are finite dimensional spaces. Okay. So, we are not working with any infinite dimensional spaces. So, because this is an operator on finite dimensional space, we have the eigenvalue for phi. So, now look at phi minus lambda identity V. So, this is a map from V to V, and this is also a G module map. So, this is also a G module map. Now, note that the kernel of phi minus lambda identity V, so this is going to be non-zero kernel, and that forces that this phi minus lambda identity V is exactly 0. That is because the kernel being non-zero submodule of V, V is being irreducible, that forces that the kernel should be full. So, the map should be the 0 map, that forces that phi is exactly lambda times identity V. So, that means the home space of all G invariant maps, that must be one dimensional, which is exactly spanned by identity. Now, let us look at the third statement. So, let us say xi being the non-trivial isomorphism from V to W. Okay. So, now if we take any phi from home G V comma W, so then we have the following map. So, we have V to W phi. Now, from W to V we have this xi inverse. So, by composing it we have a map from V to V. Okay. So, by composing phi psi inverse, we have a map from V to V. Now, from previous analysis we can see that xi inverse phi must be some A times identity. So, that forces that this phi is nothing but okay, A times xi identity V. Okay. So, that means this phi is in the C span of xi. Okay. So, xi is V to V, this is identity. So, if you are, yeah, we can actually the inverse we can take. So, it should be written the other way. Yeah, all these are multiples of some maps, okay, that says that the dimension of home G V comma W is just 1. Okay. So, these forms of Schur's lemma is very important. Okay. It basically says if you take any non-zero map from two irreducible modules, that must be isomorphism. From that we can conclude that whenever V is not isomorphic to W, there is no non-zero G module map from V to W, and similarly whenever V equal to W, then the scalar multiple of identity is the only thing, and V is isomorphic to W, then up to like a scalar there is a unique non-zero G module map. Okay. So, how one can actually use this to conclude anything? So, we can actually have various applications. So, let us actually see one by one. First of all, if we take some element from the centralizer of G, then we can immediately see that that element should act as scalar on any given irreducible module. Okay. This is the corollary 1, which is again very easy to prove. So, let us again start with the V being a finite dimensional G module, and let us take x from the centralizer of G. Okay. One can more generally, if we know what is universal unpairing algebra, then one can take x from the universal unpairing algebra. Okay. But anyway, we will introduce the universal unpairing algebra in the later classes. Now, for time being, you can take it to be the center of G, which is by definition those y in G that commutes with all the elements of G. Okay. So, now x, we can look at the x action on V. Okay. We can prove that x acts as scalar on V. Okay. So, this is just immediate from the Schur's lemma, because the action of x obviously commutes with the action of g. So, that means it is defined a G module map from V to V. So, if x is 0, if x acts as 0, then there is nothing to prove. If x acts as non-zero element, then it must be some non-zero scalar multiple of identity. So, here is the corollary 2, so which is the more important corollary. Okay. So, we can actually determine the isomorphism classes of irreducible models over GLN using the information about the isomorphism classes of irreducible models over SLN. So, basically we have the following bijective correspondence. If we take isomorphism classes of irreducible finite dimensional GLN modules, so then there is a natural one-to-one correspondence between this and C cross isomorphism classes of irreducible finite dimensional SLN modules. Okay. So, now this one-to-one correspondence will tell you that to classify all the irreducible finite dimensional GLN modules, it is enough to classify irreducible finite dimensional SLN module. So, we will use this correspondence very much. So, how one can prove? So, this actually immediately comes from the relationship between GLN and SLN. So, note that GLN is nothing but, so one dimensional center direct sum SLN. Okay. Even as a Lie algebra, this decomposition is there. So, this identity matrix n by n matrix, this is in the center of GLN. So, this is something we have seen already. Now, if we take V being irreducible GLN module, okay, then you can see that this identity will act as some scalar on this capital V. So, that means this action of identity on V will be just some scalar times identity on V. Okay, we are looking at the action. So, now we can take this V and then associate this lambda, and as well as we can see that the restriction of this module to SLN, it is going to be irreducible. So, we can look at this restriction of GLN to SLN, same module as a vector space V, we just restrict the action. So, this is going to be irreducible SLN module. So, why this is true? That is just a simple verification. Suppose W is a submodule, SLN submodule, okay, I will leave it as exercise, it is very easy. Then that implies that W is GLN submodule. Now, because it is GLN submodule, so it should force that W being either 0 or V. It cannot be 0 if you begin with non-zero module, then it has to be exactly V. That forces that V being irreducible SLN module. So, that is because only the difference is the action of identity matrix n by n matrix. So, that actually acts as scalar. So, there is no much difference between the action of GLN and SLN. So, now you can take the isomorphism classes of V and then send it to this lambda V and then comma the restriction. Okay. So, this is the map that we have here, and it is easy to see that this map is injective. Okay. So, now it is not difficult to actually get the converse. The converse map, you start with any scalar A from C and irreducible representation, irreducible SLN representation capital V. Then one can extend the action of SLN to GLN in a very trivial way. For example, we can take some C identity n plus dx. So, this is going to be the general element in GLN. So, then you just define the action of this element on any element of V in capital V to be just exactly equal to. So, let's use this scalar A. So, then this is exactly C A times V plus d x V. Okay. So, the identity just identity matrix n by n matrix acts as this A, that is what you are using, and remaining things you just extend the SLN action that you already have. Then it is easy to see that this is indeed defines GLN action. So, this define GLN action on capital V. So, now it is not hard to prove because this identity n by n matrix acts as scalar A. So, any GLN submodule will be SLN submodule, okay, that forces that V must be irreducible. Okay. So, this is the inverse map. So, this map we have given very explicit inverse map that tells you that this map that we have defined here, V goes to that lambda V, the restriction of GLN to SLN V is indeed bijective correspondence. Okay. So, we will use this corollary later to prove that there is a so, the problem of classifying irreducible finite dimensional GLN module will be reduced to this classifying irreducible finite dimensional SLN module. Okay. So, here is another important corollary of Schur's lemma, which actually tells about the existence of non-degenerate bilinear form for given irreducible G module. Okay. So, let me state the proposition. So, let us start with again V being irreducible finite dimensional G module. Okay. So, now if we have this situation, okay, so let us look at the bilinear space. The bilinear form, we know that this is naturally isomorphic to the home V comma V star as a G module. Okay. So, now if we look at the G invariant forms here, so then that will be definitely corresponding to the G module maps here on the right side. Okay. So, that means, so whenever you do not have actually if we do not have this V is isomorphic to V star, then we may not have any non-zero G module map from V to V star. So, that will force that there is no G invariant bilinear form on capital V that comes from this this module. Okay. So, basically what we are saying, if V is not isomorphic to V star, of course, as a G module, so then there is no non-zero G invariant bilinear forms of V. Okay. So, why? Because if we start with a bilinear form, let us call it B, which is inside the bilinear forms of V such that x b is 0 for all x in G. So, then look at this B tilde, which is a map from V to V star, which sends V to B of V comma dash. So, this is a G module map. If B non-zero will imply that B tilde is non-zero, then that will force that B tilde is an isomorphism using the Schur's lemma. Okay, this is coming from the Schur's lemma. So, that means this V and V star must be isomorphic. So, if you start with V and V dual are not isomorphic, then we may not have any invariant bilinear forms. So, now the second statement, suppose V is isomorphic to V dual. So, then the space of G invariant bilinear forms, that must be one dimensional. So, then the space of G invariant bilinear forms is indeed one dimensional. Okay, that is again comes for free from this correspondence. Okay. So, maybe I can rewrite this BL of V G, which is the invariant bilinear forms, which will be isomorphic to home G V comma V star, which is the G module maps. So, this is the G module maps from V to V star, and this is the G invariant bilinear forms. From the Schur's lemma, we know that this is one dimensional, so that forces that this is one dimensional. Okay. So, now once we know that V is isomorphic to V star, then we know that this there is at least one non-zero bilinear form. So, we can also determine whether it is symmetric or skew symmetric. Okay. So, because we already know that V tensor V star tensor V star is actually decomposes into symmetric and skew symmetric. Okay. So, because this G invariant thing is just one dimensional, okay, one can prove that it cannot decompose into two things, it has to be inside either symmetric or skew symmetric. So, how one can prove this? So, let us start with B, which is inside this invariant G form. Okay. Then it is not hard to prove B transpose is also there inside this invariant G form. Okay. So, this is simple exercise, I will leave it. So, now this forces that B transpose must be multiple of B, because the space is one dimensional. So, this is being one dimensional space. So, this is what we get for some A in C. So, now just take the transpose, then you get B transpose is B. So, that forces that this is exactly equal to A B transpose, which is exactly equal to A B again. So, this will give you A square B. So, this tells you that B is equal to A square B, and B is being non-zero, that forces that A square should be 1, that forces that A is plus or minus 1. Now, it is not hard to see when A equal to 1, then we have B is symmetric. When A is minus 1, then we have B is skew symmetric. So, this is more or less by definition, okay, because B transpose is being B is what is called symmetric, and B transpose is being minus B is called skew symmetric. So, this way we can actually guarantee that whenever V is irreducible G module, then using Schur's lemma there is always G invariant bilinear form of V. We can prove the existence of that. So, if you think about it, like one can ask, like, so is there any way to actually get G invariant bilinear form? Indeed, there is a way. Okay, if you start with V being just a G module, so then there is something called trace form that one can define. Okay. So, this trace form gives you actually G invariant form on G. Okay. So, we will be interested only on the forms that one can actually define it on G itself. Okay. Let us say G being the Lie algebra. So, one can take it to be either SLN or GLN. So, we can actually talk about the bilinear forms on G. So, that is what we are interested in. Okay. So, now if we take this adjoint representation, okay, so then one can see that the invariancy can be actually rewritten as follows. Okay. So, G acts on G via adjoint. Okay. So, you want to think G as a G module via adjoint representation. So, then we are interested in the G invariant bilinear form, G invariant bilinear form on G. Okay. So, that means if you rewrite the condition, what that means to be its G invariant, then you can see that this is exactly gives us B of the bracket x y z. So, that is the x v plus B of y comma the bracket x z, okay, that is being 0 for all x y z in G. So, now one can rewrite this as follows. So, if you just rewrite this, this can be rewritten as follows: B of x y z is same as B of x the bracket y z. Okay, this is true for all x y z in G. In most of the classical books like Humphreys and so on, so this is what given as definition of G invariant form. Okay. So, for example, Humphreys, Carter uses this definition. And of course, one can start with the definition and then just build the theory, but this approach of considering this bilinear forms on G and then we are indeed looking for the G invariant element there actually kind of motivates us to define this G invariant bilinear forms very naturally. Okay. So, now how to get this G invariant bilinear forms using some general methods. Okay. So, let us see that. So, one can start with any finite dimensional G module. Okay. So, then one has this trace form which is a map from G cross G to C. So, one can define this as follows: you take any x y and then send it to the trace of x v y v. Okay. So, where what is x v? So, you have a map from G to G L of v which is given by this G module. Then you take x and the image of that is defined to be x v. So, you take x y that is mapped to trace of x v y v, then one can prove that this is indeed G invariant. Okay. So, this B v is indeed G invariant form on G. Okay. So, let us do this computation, it is very trivial. So, fix x, y, z inside G. So, then we have, so we want to prove that B v of x, y, z is same as B v of x, y, z. Okay. So, let us compute this on the left hand side. This is exactly trace of bracket x v y v times z v. So, if you think about it, this is exactly trace of x v y v z v minus trace of y v x v z v. On the other hand, this is again exactly equal to the trace of x v times y v z v minus z v y v, and which is exactly equal to trace of x v y v z v minus trace of x v z v y v. So, if you compare them, these two things should be equal. Why? Because this term and this terms are same, and this is exactly, so you can rewrite it as, so this is A and this is B, and this is B and this is A. So, it basically says trace of AB is same as trace of BA. Okay. So, using this elementary fact, you can see that these two identities are same. So, that forces that this identity must be true, which is equivalent to BV being actually G invariant. So, this way we can actually many interesting examples of G invariant forms. So, now the very important example that actually comes from the adjoint representation. So, G acts on G via adjoint map. So, if we use that, then we get the associated trace form. Okay. So, that is the B adjoint of G. So, this is again defined to be the trace of add G of x composition add G of y. Okay. So, this is indeed called what is called the Killing form. This was first introduced by Killing, and it is now immediate that this is symmetric plus bilinear form and also G invariant. So, one can ask this question. So, when this form is indeed non-degenerate, so that is answered using the Cartan criteria. The Cartan criteria says that this form is non-degenerate, so which is also denoted by the kappa of G. Okay, we will use this notation. So, G is semi-simple if and only if the corresponding Killing form is non-degenerate. So, there is a easy way to define the semi-simple Lie algebra. So, it means G has no non-zero abelian ideal inside G. Okay. So, that is equivalent to saying that the corresponding Killing form is non-degenerate. So, later we will see that how one can actually compute this Killing form for GLN and SLN. Okay, we will also use some general theory to actually deduce how to compute this form for SLN. So, we will use this form and then use some property of that to get the Casimir element. So, that is the ultimate goal. So, we will do that in the next class. Thank you. I will stop here.